Today we discuss the completeness property. This is a very important property for real numbers. Earlier, we saw that both the real numbers and rational numbers satisfy algebraic and order properties. So how do we distinguish these two sets? The answer is exactly the topic that we are discussing today, the completeness property, which gonna separate the set of real number from the set of rational number. Now, in order to define the completeness property, we start with a few definitions. First, we talk about supremum and infimum. What are they? Here is the definition. Let S be a non-empty subset of the set of real numbers. A. S is said to be bounded above if there exists some number U such that S is smaller than or equal to U for any element S in this set capital S. Each number U here is called an upper bound of S. Priori, a set might have several upper bounds. The least upper bound, if it exists, is called the supremum. So the supremum is the smallest upper bound. Similarly, we can define the infimum. The only modification is that we replace upper bounds by lower bounds. That is, the infimum is defined to be the greatest lower bound. Again, a set of numbers might have several lower bounds. Among these lower bounds, we choose the greatest number that is defined to be the infimum of the set. Part C says that a set S is bounded if it is both bounded above and bounded below, and it's called unbounded otherwise. Here is an example. Let's consider the set of all real numbers smaller than or equal to 2. Then obviously 3 is an upper bound. Why? Because any element in this set is smaller than or equal to 2. That's why it is smaller than or equal to 3. 3 is a higher number than 2. So actually, any element in this set is smaller than 3. Similarly, 4 is another upper bound. Indeed, 2 is also an upper bound because every element in this set is smaller than or equal to 2. And in this case, 2 here is the supremum of the set because we cannot find a smaller upper bound. For any number smaller than 2, then there must be some number inside a set S which is bigger than that number. So here is the lemma which tells us how to characterize the upper bound of a set, the supremum of a set. an upper bound U in the supremum of the set S if and only if U satisfies the following condition. If V is smaller than or equal to U, then there is some number S prime in this set capital S such that V smaller than S prime. This is equivalent to the existence is this equivalent to the following statement. For any number epsilon greater than 0, there exists some number S probably depending on epsilon inside this set capital S such that U minus epsilon is smaller than this number S depending on epsilon. The proof of this lemma goes follow. Again, I would like to give a proof to illustrate how we apply the definition of this new notion of infimum and supremum of a set in order to deduce further statements about this notion. In one direction, we assume that U is the supremum of the set S, and we want to show that this condition is true. So we pick a random number V smaller than U. Then by the definition, because U is the smallest upper bound and V here is even smaller than U, then V here is not an upper bound. Then by the definition of an upper bound, there must exist some number S prime inside this set capital S such that V here is smaller than S prime because V is not an upper bound. Now for the other direction, we assume the condition is true and we want to show that U here is actually the supremum. The proof here is by contradiction. And let me emphasize that proof by contradiction is a very, very common technique that you're going to see again and again in this class. In order to prove some statement is true, we assume that it's not true, we assume that it's false, and then we deduce statements after statements until we get to the point of contradiction. So for this case, we proceed as follows. Suppose U is not the supremum of this set S, capital S, then there is some number V smaller than U such that V is an upper bound. Remember, the supremum is the smallest upper bound. V here is an upper bound, but not the supremum. So it's not the smallest upper bound. So there is some smaller upper bound. And we call that smaller number, we call that smaller upper bound V. By the condition, there exists some S prime in S in this set capital H such that V here smaller than S prime. That is clearly a contradiction to the definition of an upper bound for V. That's why the proof is complete. We assume the statement is false and we arrive at a contradiction. That's why the statement must be true. Now we are ready to define to state the completeness property. So the completeness property says the following. let me color it so that we can emphasize this notion. Okay, it says that every non-empty subset of real numbers that has an upper bound also has supremum inside this set of real numbers. So this is a very non-trivial statement. We know that a set might have several upper bounds, but we don't know whether it has a supremum because the supremum is rather special. The supremum, remember, is the smallest upper bound. We don't know if they function a number. That's why this property is so special. It says that as long as a set has an upper bound, then it has a supremum, and this supremum must be a real number. And this second part here is very important because it really explains the terminology of completeness here. Basically, it says that the real number is complete in the sense that it contains all supremums of all subsets. Now, note that the supremum of a set might not be in this set. For example, we consider the set of odd numbers or real numbers smaller than 2, strictly smaller than 2. Then we can easily show that the supremum for this set is 2. This is an upper bound, and this is indeed the least upper bound. Any number smaller than 2 will be in this set, and that's why it doesn't have, it's not an upper bound. That's why 2 is the least upper bound. That's why 2 is the supremum of this set. But obviously, this set contains all numbers strictly smaller than 2. So 2 here is not inside this subset. And again, this example further illustrates the completeness of the set of real numbers. A subset might not contain its supremum, but this bigger set, the set of all real numbers, it contains all supremums for any subset of real numbers. That's why it's called the completeness property. And this completeness property will have several consequences that we're going to discuss in the next lecture.